corners. Now we have 6 corners. Which corner is the best? That is when our objective function comes in. Okay. What we need to do is to substitute these two values into our objective function, 5x1 plus 2x2, and then get a value out of it. The point with the highest value wins. The point with the highest value wins because we are maximizing. If it is minimization, then the point with the lowest value wins. Okay. Now, before we do that, let's try to draw the objective function line first. And that is going to be important because so far we have not seen, we haven't drawn the objective function line. So how does the objective function line feature in the graphical space? Now, what we want to do is use the same trick, yeah, plus one additional trick. So what we want to do is to convert the objective function line into a line equation. And what we do is we write down, okay, but there's no inequality to begin with, right? So what do you mean by converting to a line equation? What we need to do is to just set it to some number. Just set it to some number, right? So for convenience, I will set it to a number that can easily allow us to find 2 points. Set x2 equals to 0, set x1 equals to 0, right? Remember the trick? So to do that, I will just conveniently use 5 times 2, the multiple of the two coefficients. So there's no particular reason other than convenience in finding 2 points. And we'll see why this arbitrariness, we kind of very arbitrarily just pick 5 times 2, right? Is there a reason for it? It's not so consequential because we're going to adjust it. We just let the line appear first, and then we will adjust it to find the optimal point. So when we do that, we can again quickly substitute. X2 equals to 0, x1 is 5, right? Because 10 divided by 5, we get 2. So x1 is 2, x2 is 0. Yeah. When x1 is 0, x2 is 5. So when x1 is 0, x2 is 5 over here. So very conveniently, we have now 2 points, and we are able to then draw a line. This time round, I'm going to use a dotted line with a red marker because it is important. It is an objective function line, and it's not final, so I want to use dotted line first. It's not final, and it is typical for us to indicate a direction of movement. Over here, let's understand first. This line is the objective function line, and it has got a specific right-hand side value 10. Okay, 2 things happen. Number 1, mathematically, all points, whether it's 0, 5 or 2, 0 or any point in between, they all, when they substitute on the left side, they all give rise to 10. Agree? That's how the line appears. That's why we link them all up, because of the common feature that all points evaluate to 10. Now, that is point number 1. Point number 2 is, remember, this is our profit. So, interestingly, we seem to be saying that our profit, if it's set to 10, will appear on this line. But then we can now use the graph to reverse back. If we shift the line so that 5x1 plus 2x2 equals to 9, all right, that means this line is going to shift down a little bit, or down a little bit, until it touches 0, which means 5x1 plus 2x2 equals to 0. That means our profit will be 0, right? So if we move this way down, all right, parallel, all the time parallel to our original first line, it means our profit will be reduced down to 0, which is not what we want. So in other words, the other direction will be the opposite. If we move the other way up, again, all the time in parallel to this original line, our profit will go up and up and up and up. let's say we touch this point, 4, 6. How much profit do we have? 5 times 4, all right, that's 20, plus 6 times 2, that's 12, altogether 32. So we can actually then write equals to 32. If we shift our objective function line to touch this particular intersection point, can we do more? In other words, can we shift some more to the top right while still having this objective function line touching, intersecting, all right, non-trivially with our feasible region? And the answer is yes. We can creep more to the right and more to the right. Can we do more? Yes. And can we do more? Yes. When we just barely touch this point, we know we are at the edge, because one tiny little step further, we drop off the cliff and no longer intersect any point on the feasible region, which means our boss cannot ever produce that combination of tables and chairs. Like, it will use too many man hours, it will violate one of the company policies, and so on and so forth, right? So this point therefore indicates the maximum right hand side value of the equation, and hence the maximum profit. And if we substitute 8, 3 into the left hand side, we get 5 times 8, that's 40, plus 2 times 3, that's 6. So end up we get 46. And numerically, we see that 46 is indeed a lot higher than 32, right? And we have proven that this point confirmed is the highest, because 8, 0 just gives us 40. And in general, any points that are more to the right side, are larger and more to the upwards direction, northeast direction, will give us a better profit, right? So what you need to do to illustrate your understanding in the homework exercises and all that, you should move your ruler. But drawing a whole lot of lines like this not only messed up the whole drawing, the clarity, and may not actually be better as far as presentation is concerned. So we will use this movement, all right, on our own to guide us to this point, and then we will just do one substitution will do. So as a matter of learning and illustration, I also evaluated these 2 points. You can also try evaluating the values for these 3 other points, right? Namely, you have 12, right? So this is 12, and this is 2 times 1, you get 2, right? And of course, this you get 5 times 1, and you get 5. Yeah, 1, 0, right? Yeah, okay. So as we move along, you don't actually have to evaluate all these. Just moving the virtual ruler to the right, more or less parallel, right? And then it will guide us to this point, and then we can find the intersection of this point and evaluate the value. And this must be the highest profit, and hence the optimal solution. All right. Now, so what we can do is we can just try to have a few perpendicular arrows. Right? That's why we customarily want to do this, to show that the direction of improvement in profits. Why do we want to improve the profit? Because it is maximization. If it's minimization, then we want to move in the direction of reducing the right-hand side. And that doesn't necessarily mean moving left or moving right or moving northeast, southwest. You just have to move the ruler a little bit to check out. So try not to have any preconceived idea about the direction, right? So, and then that should give you a lot more objectivity in terms of evaluating any given LP model, tricky ones or otherwise. So that's a lot to take in, and let's just do a quick summary. So we draw the lines, right, and form the feasible region. We draw the objective function and then shift it a little bit to test out which direction is according to the direction that the original problem wants. Here we want maximization, so we want the right-hand side number to increase as high as possible without leaving the feasible region. So that means in this case, top right, right, as we know that. Now, notice that in this case, if we were to look at the 3D aspects, in other words, what does this 46 mean? What does this 32 mean? Then we will have to introduce a new axis, that is the profit axis or the z-axis. So what we can do is we can certainly try to contain or flip the plane